All right, this is a case where a capacitor that's initially fully charged by a battery is then disconnected from the battery and connected to another capacitor that's initially uncharged, and then charge flows between the two capacitors. For this particular question, the battery given is 9 volts. The 9-volt battery, when switch 1 is closed, fully charges the 10 microfarad capacitor. After that capacitor is charged, switch 1 is opened, disconnecting the battery, and then switch 2 is closed, connecting the two capacitors together, and then charge flows between the two capacitors until equilibrium is reached again. The question here is to find the final charge on each capacitor when that happens. The first thing I'm going to do here is find out how much total charge is available to share by figuring out how much charge is given by the battery to the capacitor on the left. The charge Q stored by a capacitor is based on two things. One is its capacitance, which is a property of the capacitor, and the other one is the voltage given to it by the power source. So in this case, the charge is 10 microfarads times 9 volts, which is 90 times 10 to the negative 6 coulombs, or just 90 microcoulombs. The 90 millicoulombs of charge is now available to share between the two capacitors. Critical general principle is that charge flows through a conductor as long as there's a potential difference across it. So here, charge will flow from one capacitor to the other until they have the same potential difference or voltage. And the other thing I need to know here in order to solve for the charge is that the total charge, the 90 microcoulombs here, is conserved. All right, so now I'm going to solve for the total charge on each capacitor after equilibrium is reached again here. To do that, I'll call the capacitor on the left capacitor 1, and the one on the right capacitor 2. And then I'll call the charge on each one Q1 and Q2. So the total sum of the charge, because charge is conserved, has to be the initial charge available before they were connected together, which is the 90 microcoulombs initially given to the left capacitor by the battery. So Q1 plus Q2 equals 90 times 10 to the negative 6 coulombs. Now I have two unknowns here, so I do need two equations. The other one is gotten by setting the potential difference of the left capacitor equal to the potential difference of the right capacitor, and that's because charge flows until those two are equal. Since Q equals CV, the voltage on each capacitor is its charge, Q1, over their capacitance. So that's C1 for the left, and that equals Q2 over C2 for the right. When I plug in values here, I would get Q1 over, this is a ratio, so I'm just going to put 10, equals Q2 over 20. The times 10 to the negative 6 would cancel out, so I'm just going to put over 20. And from this, I get that Q2 equals 2 times Q1. And then I'll sub this in the first equation up here. And I get that Q1 plus Q2, which is 2 times Q1, equals 90 times 10 to the negative 6. And from that, I get that Q1 is 30 times 10 to the negative 6, or 30 millicoulombs. And then Q2 is 60 millicoulombs. So that's the charge stored on each capacitor. Now, the word capacitance does have to do with how much charge can be stored on a capacitor. So the right capacitor has twice the capacitance, and it also stores twice the charge. Something else about this situation, as charge is flowing between the two capacitors, there is energy lost. There's heat lost in this resistor here and in the wires. The energy stored in a capacitor is 1/2 CV squared. So down here I compare the energy before and after. Here's the energy stored on just the left capacitor by itself. And then the final energy, which is the sum of both after equilibrium is reached again, that energy decreased. And again, that energy is lost as heat.